Good day, everyone. Today, our group will discuss the database management system. This chapter deals with the database model as a particular philosophy whose objectives are supported by specific strategies, techniques, hardware, and software that are very different from those associated with flat file environment. This chapter, we drew a distinction between two general data management models, the flat file and the database model. The first section of this chapter examines how traditional flat file problems are resolved under the database approach. The second section details the functions and relationships between four primary elements of the database management system. First is the users, the database management system, the database administrator, and the last is the physical database. The third section is devoted to an in-depth explanation of the characteristics of the relational model. The fourth section concludes the chapter with a distinction of distributed database issues, and we examine three possible database configurations: the centralized, the partitioned, and the replicated databases. So, by the end of this chapter, we hope that you understand the operational problems inherent in the flat file approach that give rise to database approach. We hope that you understand the defining elements of the database environment. We hope that you understand the anomalies caused by not normalized databases and the need for data normalization. We hope that you're familiar with the stages in database design, including entity identification, data modeling, constructing the physical databases, and preparing user views. And lastly, we hope that you're familiar with the operational features of distributed databases and recognize the issues that need to be considered in deciding on a particular database configuration. So now let's discuss the flat file model. So what is a flat file model? Well, it is a single view model that characterizes legacy systems in which data files are structured, formatted, and arranged to suit the specific needs of the owner or primary users of the system. So as you can see in the table shown, every user transactions are separately stored in the respective databases. So files stored by user 1 can't be used by user 2. When multiple users need the same data for different purposes, they must obtain separate data sets structured to their specific needs. Hence, in this kind of environment, no sharing of data is taking place. So, this model faces two major problems. The first one is data redundancy, while the second one is task data dependency. The data redundancy can be further divided into three more problems. The first one is data storage. Some commonly used data under this model is stored in duplicated dozens, hundreds, or even thousands of times, creating excessive storage costs. Second one is data updating. When users maintain separate files, any such change must be made separately for each user. These add significantly to the cost of data management. The third one is the currency of information. Sometimes, under this model, especially when we are dealing with multiple updates, there could be a problem of failing to update the files of all users affected by a change. If updates messages are not properly disseminated, then some users may not record the change and will perform their duties and make decisions based on outdated data. The second problem is the task data dependency. This kind of problem refers to the user's inability to obtain additional information as his or her needs change. The user's information is constrained by the data that he or she possesses and controls. In this model, users do not interact as members of a user community. They act independently. While given the environment, it is difficult to establish a mechanism for the formal sharing of data. If a data is needed but unbeknownst to the user is located outside the access file, the user has to recreate from scratch. This will of course take time, add to redundancy, and drive data management costs even higher. So, an organization can overcome the problems associated with flat files by implementing the database model to data management. As discussed in the previous chapters, this approach centralizes the organization's data into a common database that is shared with other users. This kind of approach is possible because of the DBMS, which is a special software that is programmed to know which data elements each user is authorized to access. So, The database approach is created in order to solve the problems of flat file model. This approach resolves the problem of data redundancy, single update, current values, and task data independence. Once again, under the flat file approach, each data element is stored only once, thereby eliminating data redundancy and reducing storage costs. Since each data element is stored only once, it requires only a single update procedure. This approach also updates the data values for all other users related to the data whenever the user updates the data. Users have access to the full domain of data available to the firm. As users' information needs expand beyond their immediate domain, the new needs can be more easily satisfied than under the flat file approach. This problem solution provided with a database approach can clearly be comprehended since this approach places all the firm's information eggs in one basket. Thus, it is essential, therefore, to take very good care of the basket. The database approach has three conceptual models. These conceptual models are used for business information systems, and these are hierarchical, network, and the relational models. The first two models, the hierarchical and the network model, have certain conceptual similarities. They are often termed as navigational or structured models, because the way they are organized in these early database systems forces users to navigate between data elements using predefined structured paths. But one of their differences is that the former is established through pointers that create explicit linkages between related records. The only way to access data at lower levels in the tree is from the root and via the pointers down the navigational path to the desired records, whereas the latter, to put it simply, allows a child record to have a multiple parents. The relational model is far more flexible by allowing users to create new and unique paths through the databases to solve a wider range of business problems. In-depth explanation of these concepts will be done by the next reporters. So, the database concept has four primary elements: users, the DBMS or the database management system, the database administrator, and the physical database. Today, I will be discussing the first two elements of the database concept, the users and the database management system. The users can access database in two ways. The first is via a user application programs that systems professionals prepare. These programs send data access requests to the DBMS, which validates the request and retrieves the data for processing. Under this mode of access, the presence of the DBMS is transparent to the users. Data processing procedures for transactions such as sales, cash receipts, and purchases are essentially the same as they would be in the flat file environment. The second method of database access is via direct query, which requires no formal user programs. The DBMS has a built-in query facility that allows authorized users to process data independent of professional programmers. So, the second element of the database approach is the database management system. The DBMS provides a controlled environment to assist or prevent user access and to efficiently manage the data resource. The DBMS accomplishes the following objectives. First, program development. It contains application development software. Both programmers and end users may employ this feature to create applications to access the database. Second, backup and recovery. During processing, the DBMS periodically makes backup copies of the physical database. Third, database reporting. This feature captures statistics on what data are being used, when they are used, and who uses them. And the fourth one, database access. It is the most important feature of DBMS, which is to permit authorized user access to the database. The database management system is run by different programming languages. Each language has their own function. The programming language that I will be discussing is a data definition language. So, what is a data definition language or a DDL? It is a programming language used to define the physical database to the DBMS. It includes the names and relationships of all data elements, records, and files that constitute the database. The DDL defines the database on three levels. They are called views: the internal view, the conceptual view, and the user view. Now, to define each view, let's go first to the internal view. It presents the physical arrangement of records in the database. The conceptual view represents the database logically and abstractly, rather than the way it is physically stored. And the user view, wherein it defines how a particular user sees the portion of the database that he or she is authorized to access. So now, let's talk about how the DBMS operation works. The first step is that a user program sends a request for data to the DBMS. The call is written in a special data manipulation language that is embedded in the user program. Data manipulation language is a proprietary programming language that a particular DBMS uses to retrieve, process, and store data. Step 2. The DBMS analyzes the request by matching the called data elements against the user view and the conceptual view. As what I have mentioned earlier, the user views defines how a particular user sees the portion of the database that he or she is authorized to access. The conceptual view represents the database logically and abstractly. So, if the data matches, it is authorized and processing proceeds to step 3. If it does not match the views, the access is denied. Step 3. The database management system determines the data structure parameters from the internal view and then passes them to the operating system. So this operating system performs the actual data retrieval. Data structure parameters describe the organization and access method for retrieving the requested data. Step 4. Using the appropriate access method, the operating system interacts with the disk storage device to retrieve the data from the physical database. Step 5. The opening system then stores the data in a main memory buffer area managed by the DBMS. Step 6. The DBMS transfers the data to the user's work location in main memory. At this point, the user's program is free to access and manipulate the data. And the last step in the operation of the database management system, when processing is complete, step 4, 5, and 6 are reversed to restore the processed data to the database. So, that's it for my report, guys. Thank you so much for listening.
Hello everyone, this is Edlyn Baliwas, and first I'll be talking about the data manipulation language and query language. Second, I'll be discussing the last two elements of the database environment, which are the database administrator and the physical database. Lastly, I'll be giving a short introduction about the relational database model. The data manipulation language is a computer programming language which permits users to manipulate data in a database through the use of commands that enables them to retrieve, process, and store data. User programs may be written entirely in the DML, or users may customize universally written programs by inserting DML commands. These commands mirror simple English language, which enhances user interaction with the database. Common DML commands include select, input, and delete. Inserting these commands enables programs initially written for the flat file system to be inclined with the current database environment. Data Query Language, or simply DQL, is a computer programming language that permits end users and professional programmers to access data in the database directly without the use of conventional programs. It works by sending queries in order to retrieve data from the database and information systems. In the early 1970s, IBM developed the Structured Query Language, a fourth-generation non-procedural language with many commands that allows users to input, retrieve, and modify data easily. Because of its ease of use, it has emerged as the standard query language for both mainframe and microcomputer DBMSs. SQL, or pronounced as SQL, requires no technical knowledge and far less training in computer concepts and programming. With administrators preferring SQL, it is now an official standard recognized by the International Organization for Standards. The third element in the database environment is the database administrator. A database administrator's primary responsibility is to maintain data integrity. They are responsible for managing database resources such as backing up systems in case of power outages or other unforeseen instances. The DBA must ensure that no data can be leaked from unauthorized access while still being available to users. Aside from these, other duties of the DBA include training employees responsible for database planning, database design, database operation and maintenance, and database change and growth. The database administrator is in the center of all interactions because all transactions involving data retrieval must first pass through the hands of the DBA. The DBA interacts with the end users by providing the data that they need, and they collaborate with the management to come up with policies, procedures, and standards that is in line with the DBA's and the entire organization's goals. System professionals come hand in hand with the DBA when it comes to looking for ways to preserve data security, privacy, and integrity while still being able to accommodate the user's needs. Lastly, they coordinate with operations through providing information that is relevant to production and resource management. The data dictionary describes every data element in the database, which enables all users to share a common view of the data resource and greatly facilitates the analysis of users' needs. It is a file or a set of files that contains records about other objects in the database. The last element in the database environment is the physical database. It consists of magnetic spots on magnetic disks and is a collection of records and files. It is both the actual device containing the data as well as the paths used to access the information needed. An indexed sequential file is a type of file organization which combines both sequential file method and direct access method through the use of indexes. These indexes are used to create a cross-reference called an inverted list, which allows even more flexible access to data. Two indexes are shown in Figure 9-7. One contains the employee number or the primary key for uniquely locating records in the file, and the second index contains record addresses arranged by year-to-date earnings. The records are stored in a sequential manner based on the primary key. The relational database model is based on a model originally proposed by E.F. Codd in the early 1960s. In his model, E.F. Codd outlined 12 rules that are needed to be met in a relational DBMS. As years passed, these 12 rules are either narrowed down or used as a basis to develop a new criteria for DBMS. A system is said to be relational if, first, it represents data in the form of two-dimensional tables. Each table is used to store information about related objects. The rows contain a record with a unique key, also known as tuples, and each column contains the attributes. Figure 9-8 illustrates a table titled Customer. Tuples are the unique customer numbers, and attributes include customer number, name, address, and current balance. Second, it must support the relational algebra functions of restrict, project, and join. First is restrict. It extracts specified rows from a specific table, which creates a virtual table that is a subset of the original table. Second is project, which extracts specified attributes, which also creates a virtual table from the original table. Last is join, which builds a new physical table from two tables consisting of all concatenated pairs of rows from each table. We will now differentiate the terms entity, occurrence, and attributes. An entity is anything about which the organization wishes to capture data. It may be physical, such as inventory, customers, or employees, or it may be conceptual, such as transactions, accounts payable, etc. An occurrence pertains to the number of records that refers to a specific entity. The data elements that define an entity are called attributes.
So for the associations and cardinality, the labeled line connecting two entities in a data model describes the nature of associations between them. So this association is represented with a verb such as ships, requests, or receives. So cardinality is the degree of association between two entities. Simply stated, cardinality describes the number of possible occurrences in one table that are associated with a single occurrence in a related table. So there are four basic forms of cardinality. The first one is 0 or 1. The second is 1 and only 1. The third is 0 or many. And the last one is 1 or many. These are combined to represent logical associations between entities. The value of the upper cardinalities at each end of the association line defines the association. So for the examples of entity associations, we have here 5. The first example, let's assume that a company has 1,000 employees, but only 100 of them are sales staff. Assume also that each salesperson is assigned a company car, but non-sales staff are not. So in example 1, it shows that for every occurrence or record in the employee entity, there is a possibility of 0 or 1 occurrence in the company car entity. So when determining cardinality values in an entity association, select a single occurrence or record of one entity and answer the following question. So first question is, what are the minimum and maximum number of records that may be associated with a single record that has been selected? So for example, selecting an employee entity record and looking toward the company car entity, we see two possible values. So if the selected employee record is that of a salesperson, then he or she is assigned one and only one company car. So this particular employee record therefore is associated with one and only record in the company car entity. So if however the selected employee record is a non-sales person, then the individual would be assigned no car or 0 car. So the employee record in this case is associated with 0 company car records. So for the example number 2, it illustrates a situation in which each record in one entity is always associated with one and only one record in the associated entity. So in this case, each company laptop computer is assigned to only one manager. So and every manager is assigned only one computer. So two short lines intersecting the connecting lines at both ends depict this cardinality. So for the example number 3, it presents the relationship between customer and sales order entities. So notice that the minimum number of sales order records per customer is 0 and the maximum is many. So this is because in any given period to which the sales order entity pertains, a particular customer may have purchased nothing or purchased several times, so therefore they have many records. So from the perspective of the sales order entity, however, every record is associated with one and only one customer. So for the example number 4, it represents a situation in which each specific item of inventory is supplied by one and only one vendor, and each vendor supplies one or many inventory to the company. So for the example number 5, they just use the same example like the vendor and the inventory. So to illustrate the many-to-many association, this time the company has a policy of purchasing the same types of inventory from multiple suppliers, and management may choose to do this to ensure that they get the best prices or avoid becoming dependent on a single supplier. Under such a policy, Each vendor record is associated with one or many inventory records, and each inventory record is associated with one or many vendors. Take note here that the cardinality notation technique shown in the examples is called crow's foot. So for the fiscal database tables, fiscal database tables are constructed from the data model with each entity in the model being transformed into a separate fiscal table. So across the top of each table are attributes forming columns. Intersecting the columns to form the rows of the table are tuples. A tuple, which Claude gave a precise definition when he first introduced it, corresponds approximately to a record in a flat file system. But in accordance with convention, we will use the term record or occurrence rather than tuple. So the properly designed tables possess the following four characteristics. The first one is the value of at least one attribute in each occurrence or row must be unique. So this attribute is the primary key. The values of other attributes in the row need not to be unique. So the second characteristic is the all attribute values in any column must be of the same class. So the third one is each column in a given table must be uniquely named. However, different tables may contain columns with the same name. And the last characteristic is tables must confirm the rules of normalization. This means that they must be free from structural dependencies, including repeating groups, partial dependencies, and transitive dependencies. So for this part, this deals with why database tables need to be normalized. Why is it necessary for the organization's database to form an elaborate network of normalized tables linked together? So the answer to this question is improperly normalized table can cause DBMS processing problems that restrict or even deny users access to the information they need. Such tables exhibit negative operational symptoms called anomalies. So there are three types of anomalies: the update anomaly, the insertion anomaly, and the deletion anomaly. So the update anomaly results from data redundancy in an unnormalized table. So the insertion anomaly occurs when certain attributes cannot be inserted into the database without the presence of other attributes. And the deletion anomaly, this involves the unintentional deletion of data from a table. So for normalizing tables, the database anomalies described are symptoms of structural problems within tables called dependencies. These are known as repeating groups, partial dependencies, and transitive dependencies. The normalization process involves identifying and removing structural dependencies from the tables under review. The resulting table will meet then the two conditions. The first one is the all non-key attributes in the table are dependent on the primary key. The second one is the all the non-key attributes are independent of the other non-key attributes. So, normalizing tables has eliminated the three anomalies. First, the update anomaly is resolved because data about each supplier exists in only one location, the supplier table. So, any change in the data about an individual vendor is made only once, regardless of how many items it supplies. Second, the insert anomaly no longer exists because new vendors can be added to the supplier table even if they are not currently supplying the organization with inventory. So, for the deletion anomaly to be eliminated, the decision to delete an inventory item from the database will not result in the unintentional deletion of the supplier data because these data reside independently in different tables.
The next topic will be on how we can link normalized tables. After anomalies are deleted and unnormalized tables were split into multiple third normal form tables, the next thing to do is to link them all together via foreign keys. As a recap, foreign keys are used to link related tables together. By linking, all data and different related tables are now connected again and made accessible to users. The linking of tables depend on their association or joint cardinality. Joint cardinality are the one and one or zero, one and many, and etc. These rules in linking are called the key association rules. So what are the key association rules? The first rule will be the key in a one-and-one association. Here, primary key of both tables can be used as the embedded foreign key, since each occurrence for both tables is unique. For a better understanding, let's have an illustration. This illustration represents a one-and-one association. We could see here that the primary key of the manager's table, which is the manager's name, is embedded to the other side. This scenario is the opposite of the previous illustration. We could see that the laptop number row, which is this, is used as the foreign key to the manager's table. The last scenario will be that both primary keys can be used as foreign keys at the same time. All of these methods can be used when we link tables with a one-and-one association. Unlike in a one-and-one association, for one or zero association, it would be better to use the primary key of the one side than the zero side. Although technically possible to use the zero side, it would just create problems when searching. For example, if we use the company car as foreign key for the employee table, then it would just create a lot of null values, since not all employees have a company car. One and many association is the same as a one or zero association, wherein the primary key of the one side is a foreign key to the many side, but there is a scenario that the primary key of the many side can be the foreign key. Business rule number one is a scenario wherein each vendor supplies the firm with three or fewer different items of inventory, but each item is supplied by only one vendor. Moreover, this scenario depicts a one and many association. We could understand from this illustration that the primary key of the supplier table is a foreign key. This is what the key association rule tells us about, that the embedded key should be coming from the one side. But what if the embedded key is from the many side? This illustration states that in business rule number one, it is possible to use a reverse key assignment, which is the primary key of the many side, the part number, is embedded to the other side. Although it violates the key assignment rule, it will still work since vendors only supply few items, and the items are only supplied by one. Thus, it will not create anomalies. The next scenario illustrates the business rule number two. Here, each vendor supplies the firm with any number of inventory items, but each item is supplied by only one vendor. This business rule is a true one and many association, and the only way is to embed the primary key of the one side, which is the supplier number, to the other table. It is also impossible to do a reverse embedment in this scenario because the vendor may supply any number of items, and it will only just result to update anomalies or data redundancy. The next key assignment rule will be the many and many association. In this type of association, there is a need to create a link table. A link table is composed of primary keys of two related tables. For example, business rule number 3. Each vendor supplies the firm with any number of inventory items, and each item may be supplied by any number of vendors. Here we could see both the primary keys of both tables are present in the link table, which is the part number and the supplier number. The reason of creating such link table is because embedding a primary key to the other table is impossible, and the logic with that is same with business rule number 2. Because the vendor supplies the firm with any number of items, and each item may be supplied by any vendor, then it will just really result into data redundancy if we did not use any link tables. So what accountants must do in data normalization? Even if it's not the role of accountants to normalize table, they must have a clear understanding of the process and must be able to detect if the tables are normalized or not. It's because using data with anomalies may result to a chain reaction, beginning from creating wrong reports, which may lead to wrong management decisions. The next topic will be the steps on creating a relational database. Remember that this topic is only part of a larger system development process that involves extensive analysis of user needs, and it will then be discussed in the next chapters, chapters 13 and 14 to be exact. The focus of this topic will be the 6 phases of database design. The 6 phases of database design are the following. First is to identify entities. Second, construct a data model showing entity associations. Third, add primary keys and attributes to the model. Fourth, normalize the data model and add foreign keys. Fifth, construct the physical database. And lastly, prepare the user view. These phases are collectively known as view modeling, and it will be discussed one by one. The first phase is to identify primary entities of the business function in question. Again, entities are things that the organization desires to capture data. Another thing is that entities are represented as noun in system description. So how do we identify these entities? In order for them to be called as valid entities, they must satisfy 2 conditions, which are an entity must consist of 2 or more occurrences. 2. An entity must contribute at least one attribute that is not provided through other entities. Let's identify and test various entities to see if they are valid. First, a purchasing agent. If the purchasing agent is only one in the organization, then it has failed to satisfy condition number 1. But if there are 2 or more purchasing agents, the next problem will be to satisfy condition number 2. Assuming that there is already an existing employee table, and it has already captured data about the purchasing agents, then it has failed to satisfy condition. To pass as valid entity, we must determine a unique data about the purchasing agents. Second entity will be the suppliers. Assuming the firm has many suppliers, then it has satisfied the first condition, and because no other entities can logically provide data about the suppliers, then it has met the second condition. Third, a purchasing order entity meet both conditions, since many order will be processed, and it can provide unique data attributes such as date of order and order quantity.
So the second step in designing a relational database is the construction of a data model showing entity associations. Remember that associations represent business rules, meaning to say that relationships among businesses, whether internally or externally, shapes its business strategies. We will break down these associations, so we have to familiarize the entities at the very onset displayed in the PowerPoint. And these are the inventory, the supplier, the purchase order, and the receiving report. We go first with the zero or many-to-many association between purchase order and inventory entities. The inventory in the stockpile will be ordered multiple times or none at all in a given period. But why do we have to include the zero cardinality in the association? It is because there has to be a given time frame or a calendar year in which the product will be ordered in multiple times or none at all. As we all know, cardinality is a degree of association between entities. The second, the supplier and inventory relationship, which has many-to-many association. This means that there has to be one or more suppliers who provides raw materials to the business, but at the same time, they supply one or more inventory type. Meaning to say, the pool of suppliers offer the same type of inventory to the business. This is to avoid being behind in production in times of crisis. Like for example, the businesses or the companies of tomato products. They ensure that there are a lot of provinces or a lot of places where they can procure the tomatoes in order for them to catch up with the production and increase the production rate if they want to do so. The one is to zero or many association between supplier and purchase order entities is the third association. Since we have established the premise that a supplier may provide multiple types of inventory to the business, the company may also place none or many purchase orders but addressed to a single supplier. The one-to-one association of purchase order and receiving report does not automatically mean that each type of inventory merits a single receiving report, thus requiring multiple reports for every occurrence of a supplier. The one-to-one association defines that one purchase order gives one receiving report for a single occurrence of a supplier even if there are multiple products. Simply put, different suppliers have one receiving report for every purchase order to avoid any confusion in a database. And lastly is the zero or many-to-many associations between receiving report and inventory. This means that each receiving report may contain at least one or many types of inventory. Furthermore, an inventory may have been received many times or none at all in a given period. The third step in designing a relational database is the addition of primary keys and attributes to the model. This is a vital part in the model since this is where we try to scrutinize every transaction to be input in the database. Primary keys are things like the invoice number and the check number to which we try to identify the nature of the entity. This may be in the form of block codes, group codes, mnemonics, and other techniques that has been discussed thoroughly in Chapter 2. In the diagram presented, these are the inventory number, the purchase order number, the supplier number, and the receiving report number. On the other hand, attributes are information that describes the transaction of the entity, and this depends on the user views, meaning to say that if a stored data is not useful, then it should not form part of the database. The attributes are things that are below in the primary key in the diagram and most of the time contain transaction details. So the fourth step in designing a relational database is the normalization of the data model and adding foreign keys. So normalization in this context refers to the process of organizing data in the database and ensures that data is stored logically, while a foreign key is used to link two tables together. So normalization comes in a process as seen in a diagram, and as we progress, we simplify and deduct information that doesn't serve its purpose in the database. Moreover, we will also discuss the hierarchy of normal forms that's very vital in the database. So the first thing that we have to do in normalizing data table is to simplify all the information from the sales invoice and sort it out in a single table presented in the following slide. So the sales invoice as presented will serve as a user view and a source document for us to normalize the data table and continue with the process. You will see in the diagram presented the repeating group data and the redundant data that needs to be removed. Repeating group data is the existence of multiple values at a particular attribute in a specific record. We then have to remove the repeating group data and allot table for each. The first table will be the sales invoice table with invoice number as the primary key, and the second table is the line item table which has a composite key of invoice number and product number. This too is necessary because the product may have been sold to other customers, and this will serve as a determinant to not be able to be mixed up with other transactions. Division results in the first normal form that contains a single table and does not contain repeating group of columns. It doesn't end there, as we still have to remove the existing partial dependencies. But since sales invoice table has a single primary key, it is considered in a second normal form. So, what is a second normal form? A second normal form, if it is in a first normal form, and every non-key column is fully dependent on the primary key. So partial dependencies, as seen in the diagram, occur where one or more non-key attributes are defined as part only of the primary key. And since the composite key has one or more attributes, partial dependency exists since description and unit price are not affected wholly by the invoice number. We can narrow it down into two tables, the line item table and the inventory table. For example, these two tables are now in the third normal form that defines each primary key by its attributes. And third normal form is defined if it is in the second normal form and the non-key columns are independent of each other. So in any case that there is transitive dependency, which occurs in a table where a non-key attribute is dependent on another non-key attribute and independent of the primary key, then it has to be removed. In our example, invoice number has nothing to do with the customer details. However, the customer details is of importance depending on the user view. So we have to split it up and create another table to resolve the dependency and generate a third normal form at the end of the day. So the fifth step in the designing of the relational database is the construction of the physical database. But what exactly is a physical database? It is the lowest level of database containing magnetic spots on magnetic disks. In this step, we will examine how the user will access the database and refine the database design by asking questions like, what data will I commonly use and which columns in the table should I index based on the data access? As you can see in the diagram, we can see the relationships of primary keys in different tables and how it serves its purpose together with the attributes. The dotted lines represent the primary key and the foreign keys that links together the tables in the database. So the last and final step of designing the relational database is the preparation of the user view. So as defined earlier, user view is how the user sees the portion of the database that he or she is authorized to access. In this step, this is where the SQL languages or the query languages comes into play that has been discussed in the elements of the database. This may be like the select function, the from function, and the where function. The designer simply points and clicks at the tables and attributes in the database. From the visual presentation, the database management system generates the SQL commands for the query to generate the view. So in relation to the designing of the relational database and the manifestation of the user view, there's what you call global view integration. View integration is the combining of all the data needs of the users into a single schema or enterprise-wide view. This is to create a user-friendly and a data business-wide data sharing that will be utilized for all the users of the database. So the database designer must produce a set of integrated tables that has been free from anomalies that we have done step by step earlier in order to suit the needs of the database users.
A centralized database is stored, maintained, and located in a single location such as a mainframe computer. It is maintained and modified from that location only and usually accessed using an internet connection such as a local area network or a wide area network. Under the centralized database approach, remote users send requests via terminals for data to the central site, which processes the requests and transmits the data back to the user. The central site performs the functions of a file manager that services the data needs of the remote users. As can be seen from the figure above, all the information for the organization is stored in a single database, which is known as the central database. Some advantages that can be obtained from using this approach are: number one, the data integrity is maximized as the whole database is stored at a single physical location. This means that it is easier to coordinate the data and it is accurate and consistent as possible. Number two, the data redundancy is minimal in a centralized database. All the data is stored together and not scattered across different locations. So it is easier to make sure that there is no redundant data available. Number three, since all the data is in one place, there can be stronger security measures around it. So the centralized database is much more secure. 4. The data is easily portable because it is stored at the same place. Number 5. The centralized database is cheaper than other types of databases as it requires less power and maintenance. Lastly, all the information in the centralized database can be easily accessed from the same location and at the same time. However, some disadvantages of the centralized database approach are: number one, since all the data is at one location, it takes more time to search and access it. If the network is slow, this process takes even more time. Number two, since all the data is at the same location, if multiple users try to access it simultaneously, then it creates a problem. This may reduce the overall efficiency of the system. Lastly, if there are no database recovery measures in place and a system failure occurs, then all the data in the database will be destroyed. In contrast to centralized database management system, distributed data processing is a computer networking method in which multiple computers across different locations share computer processing capability. Computers that comprise a distributed data processing network are located at different locations but interconnected by means of wireless or satellite links. In DDP, specific jobs are performed by specialized computer which may be far removed from the user and or from other such computers. Processing data in a distributed environment helps accomplish a task in a significantly less amount of time as opposed to when running on a centralized data processing system, solely due to the reason that here the task is shared by a number of resources or machines and executed in a parallel way instead of being run synchronously arranged in queue. Since the data is processed in a lesser time, it is cost effective for businesses and helps them to move fast. Data currency is the state when the firm's data files accurately reflect the effects of its transactions. When processing accounting transactions, account balances pass through a temporary inconsistency where their values are incorrectly stated until after the completion of the entire transaction. This can lead to a permanent corruption in the entire database. To illustrate, we can see that in the interval between the execution of transaction 3 and transaction 4, the AR control account value is temporarily inconsistent by the sum of 2,000. By the end of the entire transaction, the balances are correctly stated. To achieve data currency, simultaneous access to individual data elements by multiple sites needs to be prevented. The solution to this problem is to use a database blackout, which is a software control that prevents multiple simultaneous accesses to data. Databases can be distributed using two techniques. The first one is the partition database technique. In this approach, the central database is split into segments or partitions that are distributed to their primary users. A database partition consists of its own data, indexes, configuration files, and transaction logs. Because data is distributed across the database partitions,
You can use the power of multiple processors on multiple physical machines to satisfy requests for information. Data retrieval and update requests are decomposed automatically into sub-requests and executed in parallel among the applicable database partitions. The database manager allows you to store data across several database partitions in the database. This means that the data is physically stored across more than one database partition and yet can be accessed as though it were located in the same place. Applications and users accessing data in the multi-partition database are unaware of the physical location of the data. The partition approach works best for organizations that require minimal data sharing among users at remote sites. Some advantages of this approach are: number 1, strong data at local sites increases users' control. Number 2, permitting local access to data and reducing the volume of data that must be transmitted between sites improves transaction processing response time. And number 3, partition databases can reduce the potential for disaster. By having data located at several sites, the loss of a single site cannot terminate all data processing by the organization. There may be times that multiple sites will lock out each other, thus preventing each from processing its transactions. This is what we call the deadlock phenomenon. In the figure, there is mutual exclusion to data, and the transactions are in a wait state until the locks are removed. This deadlock can result in transactions being incompletely processed and corruption of the database. A deadlock is a permanent condition that must be resolved by special software that analyzes each deadlock condition to determine the best solution. Resolving a deadlock usually involves sacrificing one or more transactions to give way for the completion of the processing of the other transactions in the deadlock. The preempted transactions must then be reinitiated. In preempting transactions, the deadlock resolution software attempts to minimize the total cost of breaking the deadlock. Some of the factors that influence this decision are: 1. The resources currently invested in the transaction. This may be measured by the number of updates that the transaction has already performed and that must be repeated if the transaction is terminated. Number 2, the transaction stage of completion. In general, deadlock resolution software will avoid terminating transactions that are close to completion. Lastly, the number of deadlocks associated with the transaction. Because terminating the transaction breaks all deadlock involvement, the software should attempt to terminate transactions that are part of more than one deadlock. The second technique in distributing databases is replicated database approach. Database replication is a technique through which the entire database is exactly copied to, transferred, or integrated with more than one site. Database replication is done to provide a consistent copy of data across all the database nodes. It also removes any data redundancy, merging of two databases into one, and updating slave databases with outdated or incomplete data. Because common data are replicated at each site, the data traffic between sites is reduced considerably. Users can access data relevant to their task without interfering with the works of others. Data access for query purposes is ensured, and lockouts and delays because of network traffic are minimized. There can be full replication, in which the whole database is stored at every site. There can also be partial replication, in which some frequently used fragments of the database are replicated and others are not. Data replication encompasses duplication of transactions on an ongoing basis so that the replicate is in a consistently updated state and synchronized with the source. Database concurrency is the presence of complete and accurate data at all remote sites. To achieve this, system designers must implement methods to ensure that transactions are in such state. Concurrency control protocols can be broadly divided into two categories: The first one is lock-based protocols. Database systems equipped with lock-based protocols use a mechanism by which any transaction cannot read or write data until it acquires an appropriate lock on it. Lock-based protocols manage the order between the conflicting pairs among transactions at the time of execution. The second one is the timestamp-based protocols. In this protocol, every transaction has a timestamp associated with it, and the ordering is determined by the age of the transaction or the execution of the transaction. A system-wide clock is used to keep all sites, some of which may be in different time zones, on the same logical time. Each timestamp is made unique by incorporating the site's identification number.